doing problem 5 from practice exam 2. So this asks us to find the orthogonal trajectories for this family of curves. So well, first of all, we need to find the differential equation that represents this particular family of curves. So we'll take its derivative, which is exactly the same as the function itself. And then remember that we have to put this thing in terms of k. So k is equal to y over e to the x. And then if I plug that in for the k there, I'm going to get dy dx is equal to y over e to the x times e to the x. And then the e to the x's here can cancel, so we're just left with this differential family of functions defined by this differential equation here. Okay, so in other words, if you were to graph that family of functions right there, it would be the same as this. Okay, so if you would draw the slope field here, all of these functions here would match that particular slope field. Okay, and you kind of have an idea of what those functions are going to look like. In fact, we can just draw a little bit here about what that's going to look like. K e to the x, we just have various values of k. We're going to see our functions doing something like this. Just a bunch of exponential functions for various values of k. If k is negative, they'll go negative. So that's kind of what the family of functions will look like. And we're looking for the family of orthogonal functions, so that would be orthogonal trajectories, meaning that all the functions that we are looking for are going to be crossing through these functions at right angles. Okay. So what we want to do then is realize that this, again, is a slope field that would be generated by that differential equation here. These functions would match that slope field. But we're looking for the orthogonal ones, which means perpendicular. So we want to have a slope field of functions that is perpendicular to this slope field. So what we want to do is find the solutions to the differential equation where these slopes are the negative reciprocals. Okay, so that would be this. And then we'd like to solve that differential equation there and find the family of functions that would match this one. And that would be the ones that are orthogonal to this one. So we can do this by separation of variables. So we'll multiply both sides by y. We'll get y dy is equal to, and if I multiply the other one by dx, I'm going to get negative dx. And then I can just put the integration symbols here, and we'll get 1/2 y squared is equal to negative x plus some constant. Now if I solve this thing for x, that's probably the best way to do this. I'll get x is equal to negative 1/2 y squared plus some constant. Okay, and this is a fine way to leave this family of equations. You can kind of see what this would give you. X equals negative 1/2 y squared. That's going to be parabolas that are opening to the left. So if I, for example, just picked a parabola that opened to the left, we can kind of see that indeed it appears that it would be crossing these functions at right angles. Okay, so the plus c here, that means since we're talking about an x equals some function in terms of y, the plus c is actually going to be shifting it to the right or to the left. That's why if I draw one, if I want to draw another one, I just move the vertex to either the right or the left. Okay, so we found our family of orthogonal functions that would be orthogonal to that thing. Okay.